Okay, now let's take a look at a special case where we have two objects of the same mass. And actually, we'll even say they have the same speed here too. So we have two identical objects with the same magnitudes of momentum but opposite directions, and we'll take a look at what happens if they stick together and what happens if they bounce off of each other. So if they're perfectly inelastic and if they're perfectly elastic. And it might be intuitive if you have these two objects, with both of them mass m and a speed v that are coming towards each other, and they stick together. We might think that okay, so we have a mass of 2m now that stuck together. It might be intuitive that it's just going to stop, right? If the two of them collide together, stick together, and which it will, and we'll show this mathematically. And then also, if it's perfectly elastic, then we would actually expect them to rebound with the same speed but opposite direction. And this is again, because they have the same mass there. But let's go ahead and write this out and actually solve it and show that these are the cases of what will happen. So, like any collision with conservation of momentum, we'll start out with a coordinate system and a before and after. So in before, we have, I basically just drew this a second ago. We have both of them have a mass v and they have the same speed, a mass m, and they both have the same speed v, like this. And for case A, for part A here, they're going to stick together after, and so we have 2m like this, and we don't know what v final is. Right? But we do know that they both share the same velocity after because they stick together, right? Writing out the conservation of momentum for perfectly inelastic collisions, we have here this initial momentum here equals this final momentum here. And so we have mv plus m times negative v is equal to 2m times v final, right? And so we actually see here, it's fairly obvious, mv minus mv, this is equal to 0. And so we have 0 is equal to 2m v final. Clearly the mass is not equal to 0, right? Otherwise, it wouldn't be a very exciting collision. And so then we see from this that 0 is equal to our final velocity, which is what we would expect given that they're both the same mass and the same speed colliding head on. For part B, let me just revise this. So for part B, we'll have mass m here and mass m here. And why don't I call them different objects? This is A, this is B, and I don't know what VA final is or VB final, right? I'm not really sure, and I don't even know the direction. I'm not going to assume that I do know the direction. For part B, writing out since it's perfectly elastic, we actually have two equations we can use, right? And we have two unknowns now, VA final and VB final. So we have two unknowns. We need two equations. And generally, the easiest equation to start out with is the conservation of kinetic energy, which reduces down to, we have VB final minus VA final is equal to negative VB initial minus VA initial. And so this is VB final. We don't know these. VB final minus VA final is equal to negative of VB initial, I think was negative V, right? So that was based on my coordinate system here, that's negative V, and VA initial was a positive V. So this is negative of negative V minus V. So that's negative 2V, and this makes it a positive 2V, right? So we end up here with VB final is equal to VA final plus 2V. And then I can plug this into conservation of momentum. Right, so now conservation of linear momentum. We have the mass of A times velocity of A plus mass of B, velocity of B, all in the initial condition, is equal to the mass of A times velocity of A plus mass of B times velocity of B in the final condition. All the masses are m, so I'm going to go ahead and replace all those masses with m, and I also know VA initial and VB initial, so let me go ahead and make these substitutions. Actually, I'll go ahead and substitute this in for VB final as well. So what this comes out to is that we have mv plus m times negative v is equal to mva final plus m times, was it VA final plus 2V? Of course, this cancels out again. The initial momentum is 0 in both cases. And so we end up here with I'll combine these together. That'll give us 2mVA final, and subtracting 2V from both sides, negative 2V equals 2m VA final. Oops, this should have, I apologize, there's an m to distribute here as well. So negative 2mv, and dividing by the 2 and m on both sides, we have VA final is equal to negative v, which is exactly what we expected. A was the one that was initially coming in to the right, and so it's going to bounce back to the left with the same magnitude as it was coming in. And this is, again, only because of their equal masses there. And when I say plug in to, so VA final is negative V, once we plug this in for VB final, then VB final will be negative V plus 2V. So we get here VB final this is just equal to a positive V, which again, just like A, this is it's bouncing back the opposite direction in which it came. Again, what we expected when we have equal masses colliding, we expect them to rebound with the same speed that they came in at. But again, this is only because we had equal masses.